Okay, so I hope everybody had a great reading week. I first thing I want to do is apologize that lecture 6 was recorded from last year. I believe you guys are owed new lectures every year. Forget the fact that, the things I'm teaching have barely changed in 100 years. The codes tweak things every few years. And we'll talk about one of those things that got tweaked in the past 3 years in this lecture. But for the most part, the concepts are very relatively consistent. But I believe that it's important to record new ones each year because it allows you to know that I am taking back feedback from you, trying to incorporate things I've heard. Each year, the goal is to make it better and better and better. That said, in past years, there was always something that would cause at least one lecture to be missed. One year I had to go to Germany. One year I had to go to Helsinki. One year there was a snowstorm. There was the year the train I was on had a pedestrian fatality. There was the year I had a baby. The other year I had a baby. The year my husband was hit by a car. So there was the time I had scarlet fever, which really only happens in the Velveteen Rabbit and the Little Women, and me apparently. So there was always at least one lecture that got missed, which meant we only got to do 11 out of our 12 lectures. So this one of the good things about having this ability to record lectures or use past lectures is that you guys didn't have to miss a single bit of information. But I do want you to know that I apologize, and it's not the goal, and I really try hard not to let that happen. Last week, one of our kids had some gastro issues, so forget COVID. You're not allowed to send your kids with that at all, ever. Pre-COVID, that was the big no-no. You could send them with almost anything else, but not any gastro issues. And then we kind of had breathed a sigh of relief, and Saturday night we had friends over. It was fantastic. We had a good night, and on Sunday, 2 of their kids tested positive. So we are currently semi-isolating. Myself and Dave and our 5-year-old technically don't have to isolate because we're all double vaccinated, but our 3-year-old is obviously not vaccinated yet because they don't have a vaccine. So he is in isolation, which essentially puts me in isolation. All that to say, you may see small children running around once again. Here we are for the third or fourth week out of our 7 weeks. It's kind of getting crazy at this point. So one thing that wouldn't have been in last week's lecture because it was I find that the volume is, I can see my, too much. I'm going to just test this. That seems like it's in the good mix right there. One of the things that I had wanted to add to lecture 6 for you guys, I didn't get to because obviously I used a recording from last year. And so this is a video of my 2 kids over the summer on one of those big yellow swim mats. And what I really like about this is it shows you what is happening in an earthquake. So watch this video, because imagine my kids, it's going to do that stupid thing where the mouse is barely visible. We'll see if it does it in the PowerPoint. If it does, I'll change it. So you can see, imagine my kids are a building, and the yellow mat is the ground, and Dave is acting like the earthquake, because this is essentially what happens. So you can imagine that if a building isn't properly connected to the ground, the building can tip over, or if you don't have a lateral load resisting system. Now, what if the boys had been turned sideways and spread their legs? I tried to get a video of them doing that, but to try to get a 3-year-old and a 5-year-old to listen to you when you're standing on the shore with a camera is absolutely impossible. But that's my goal for this summer, is to get that same video with them turned with their feet spread into a triangle. And I did get them to do it once, but I didn't have the camera recording. They didn't tip over. And that is the point of our lateral load resisting system. You triangulate that load resisting, or that path for the load, and you can have a stable structure even when the ground is trying to be yanked out from underneath you. Okay. The other thing I wanted to talk about quickly is the project. So the project information for you has all been posted. So we know we have our weekly assignments. There are 10 weekly assignments, which you guys have been working on, and the 7th one gets posted on Thursday. So I don't know what day you're watching this. So it gets posted on the 3rd of March. The last 2 weeks, there aren't submittable assignments, but there are assignments that you can practice on that have worked out solutions that will be posted, and that covers our 12 weeks. The project has 2 parts, part 1 and part 2. Part 1 is where you pick a static object. Static means staying still. It is not moving. This pen, not static. This pen, static. So those are 2 different things. We want to talk about it when it's static. That is the point. We want our buildings to stay still. Now, I believe it's next week that we really start to talk about what that means. And I'm going to show you how we draw that. And I'm going to teach you a means of drawing and proving that something is static with no math. You just need to do a drawing. Then I'm going to teach you to use the math to prove that it's static. Okay? And so we're going to go through that. For the project part 1, you just have to do the drawings. And those are called free body diagrams. You don't have to do the math. You're going to talk about some things that would maybe go into the math, but for the part 1, you don't have to do math. You have to do drawings. Part 2, I have created a building for you that has been posted online in your project module. And within that project, if you look at the title block, I guess title block for the way you're seeing it, there is a list of student numbers and assigned members. You don't know how to do anything with those yet, but over the course of the next several weeks, you are going to learn how to figure out the loads on the building, figure out the factored loads, figure out the tributary area, figure out the maximum loads on each element, then look at the axial loads, the shear loads, and the internal moments, draw the diagrams, and then tell me what the worst factored loads are on each one of those elements. And that's going to be the goal for the end of this course. Next term, or when I see you in a year, we're going to figure out the reduced capacity of the members we pick to actually use there. Right now, we have an unknown member. We're guessing, because we're using our sizing guidelines, we might guess what size member it is, but we don't know if that member is right or not. Next term, we will figure out exactly what member is right. This term, we have to figure out what all of the internal loads are on those elements. Okay, so let's dig in to lecture 7 then. So there was a few more kind of less common loads that I wanted to discuss with you. And then we're going to talk about how we combine these loads. Because if you remember, you know now how to figure out the dead load of that table. You know, it's got a thickness and there's some published value for wood weight, and you could figure out how much that table weighs for every square meter of its surface. And then if we said, you know what, there could be a party on that table. You know that it needs to support 4.8 kPa. Or maybe we're going to use it in some other application. So we'd have to figure out what live load. Now, it's not a building, so I'm obviously exaggerating with the live load on it. But if it was a building, you know how you can look up what the loads are, or the live loads are, depending on what type of building it is. But we know that there's dead load on that, and there's live load on that, and there is, what if we put it outside? What if there's also snow load on that? So do we use just the dead and live, or just the dead and snow? Do we use dead, live, and snow? What if we got it wrong on the live load? What if we had more people on there? What if we got the dead load just a little bit wrong? What do we do in those cases? So that's when we're going to talk about factored loads and load combinations. And we will do some examples. So yeah, my mouse is doing the weird thing. So let me make it so that you guys can see my mouse here. It does it every now and then. Normally I don't have to adjust it. Last year I always had to adjust it. Come on, mouse. Additional mouse options. No. Just mouse cursor. Okay, so it looks like you can see it now. Okay, once it's not working, it doesn't work until it's gigantic. There's no in between. So I probably need to reset my computer, which I'm not going to do right now. So I apologize for the ridiculously large mouse. Okay, so I talked about the project. One of the things I did do for part 1 is I posted an example. I put almost no work into it because I'm the professor. I know what needs to be done. That was a very lazy version of it to try to show you a basis of what I'm looking for. You guys are architecture students in one of the best design architecture schools in the world. Use your imagination. Be inventive. Be creative. Think about what could happen to your object. Try to pick a cool object. I know at least 10 of you are going to pick a basic table. I can't mark you wrong for it, but I'm certainly not going to have any desire to give you fantastical points because of that. There is the part that needs to be correct, but there is the part that also needs to think about the fact that we're a design school, one of the best design schools in the world. So use your creativity in part 1. Part 2, don't be creative. Just do the work right. And so that's where I'm trying to find the balance for you guys. I wanted to give you guys at least a portion of a creative outlet within the structural scope, because I think that's important too. And a thing that engineers tend to forget about is that there is a creative side to things. All right. So one of the loads we haven't talked about yet is soil pressure. Now, you've heard me say before, if you've ever been at the beach and you dig a hole in the sand, that soil wants to fall back into the hole. You might dig a hole and it's absolutely perfect, and then somebody comes along and stands at the edge and all of a sudden it falls in. And we talked about that when we talked about the live loads adjacent to basements. So you can imagine if there is a big live load right here, it wants to push that soil in. Well, there's also the weight of the soil trying to push the soil in here. So that means up at the top, there's not a lot of pressure on this wall. But as you go down, more tries to push into the building. So it is dependent on the weight. Now, some of that information is going to come from a geotechnical engineer. What is the weight of our soil? And that's this value right here. So the weight of the soil in this example is approximately 20 kilonewtons per meter cubed. Usually it's around 20 kilonewtons per meter cubed, but a geotechnical will tell you exactly. This is the depth of our basement. And then there is something called the sticky factor, or I call it the sticky factor. So as that soil's trying to push down and push in, the stickier it is, the less it's going to try to push in. Buddy, I'm recording a lecture. No. It's not time for snacks. You have to go in the other room, buddy. I know. It's a hard life. So if it's kind of cohesive together, it would be like setting a blob of Play-Doh. It's less likely to try to flatten out than flour or sand, say, which would try to flow out. So the stickier it is, the less likely it is to try to fill in this hole. So that is what we call the earth pressure coefficient. And that comes from the soils report as well. So the pressure due to soil and groundwater, P, is K times Q. So K is our sticky factor. Q is our surcharge, or our live load that's happening up here. So if it's just a sidewalk, it's 4.8 kPa because we have our normal live load requirements. If a fire truck could be right here, well then we've got 12 kPa of surcharge. Gamma is the weight of the soil, and it's usually around 20 kilonewtons per meter cubed. And H is the depth below grade. So right here, our height is 0, which means this side of, or this portion of the equation goes away. That means the only pressure trying to push the soil into this basement here is our surcharge load. As we go down, here we have this much weight of soil and the surcharge. Right here, we have this much weight of soil plus the surcharge. And down here, we have the weight of all the soil plus the surcharge. And that means that at the top, we have very little pressure trying to push in, and at the bottom, we have a lot of pressure pushing in. Now, this wall here has a floor that stops it from tipping over. If this wasn't here, it would be a retaining wall, and we'd need something very large here to stop this from tipping over. All right, let's do a quick example. I'm just going to check that my son shut the door. He did not. Okay, so sorry about that. If the door's open, if the door's shut, it at least gives them the tiniest desire to rush in here. They see it open and they come running in. Okay. So the building previously discussed, I'm assuming the building that we talked about last week, has a 2-story deep basement, each one being 4 meters deep. The laneway adjacent to the building could be used for fire truck access. The geotechnical report states that the weight of the soil is 19 kilonewtons per meter cubed. So that means every meter by meter by meter cube of soil weighs 19 kilonewtons. So a stack of soil a meter tall by a meter wide by a meter long is going to weigh the equivalent of about 19 Arnolds. And our K, or our sticky factor, earth pressure coefficient, is 0.3. So these two things were given to us from the geotechnical report. What is the soil pressure in kPa at the top and the base of the foundation wall? So let's do this example here. Okay. I apologize, my kids are very, very loud today. Okay. All right, so I always find that if it's something that doesn't have a picture, to draw a picture. I find drawing pictures very helpful. And like I said, over the next few weeks, we're going to spend a lot of time actually drawing pictures. So this is our soil pressure example. Okay. So here's our building. There was some building up above here, and we know that there is the ground floor here, and then 4 meters down there was another floor, and 4 meters down is our basement. So let's just draw something to represent our floors here. Here's our basement. We've got some sort of footing here. And here is our foundation wall. And here is soil. And there's some building up here. All down here is soil. And this is soil. They have told us that this could be used for fire trucks. Do you like my fire truck? Yeah. This is why I'm an engineer and not an architect. Okay, so we know that the equation for earth pressure is P equals KQ plus K gamma H. K, the geotechnical report gave us as 0.3. Gamma, the geotechnical report gave us as 19 kilonewtons per meter cubed. Q is the surcharge. Well, if it can have fire trucks out here, fire trucks we know have a live load of 12 kPa. All right, so we could have up to 12 kPa of live load out here. So we need to design this to resist the surcharge of 12 kPa out here. And then we have, so that gives us our K, our Q, our K, our gamma. We have two different H's. We had H at the top that we needed to calculate, and H at, or sorry, not calculate. We had H at the top, which is 0 meters, because we're right here, and H at the bottom. They told us that each story was 4 meters. And what we're looking for is the pressure at the top and the pressure at the bottom. I'm not very focused for some reason. All right, so P at the top, well, our K regardless is 0.3. Our Q regardless is 12. Our K is 0.3. Our gamma is 19. And H at the top is 0. So the pressure at the top is 0.3 times 12 plus 0.3 times 19 times 0. And we have 3.6 kPa. So the pressure pushing in right here at the top is about 3.6 kPa. Let's look at the P at the bottom. All right, we still have 0.3 times 12 plus 0.3 times 19 times, this time we're all the way down here at the bottom, or 8 meters. So we have 0.3 times 12 plus 0.3 times 19 times 8 equals 49.2 kPa. So what we're saying is we have this wall that is 8 meters tall, and right here we have pressure pushing in. Up here it's 3.6 kPa, and down here it's 49.2 kPa. If this is my wall, what's stopping it from sliding this way? Well, we know right here we had the basement. Right here there's some second floor basement or second basement, and right here we have the ground floor. So this pressure is trying to push in, and the wall is going to bend between these spots and bend between these spots. And that's all the question has really asked us, is what are these values here? So here it is worked out for you as well in the slideshow. So feel free to take a look at this at your own on your own time scale if you want. Oh, my fire truck was equally bad in that version of drawing it. Okay. Okay, and here it is worked out, typed out, just so you can see it nicely if you find you have a hard time with my handwriting. Okay, let's come back up to me. All right, so what are some other load types? Now, these ones are less common and ones that we don't tend to worry about as often in design. That doesn't mean they don't exist. They can be very important in design. So one of the big ones is temperature. Steel expands when it's hot and contracts when it's cold. Most of the time, or for the life cycle of most buildings, our steel is inside an envelope. So its temperature variation is, maybe 16 degrees to 30 degrees. Most places have air control systems of some sort. So the steel in the building would be kept at in a relatively narrow margin of temperature. It often has a big impact on either I'm drawing a blank on the word, where you don't have an air system inside your building, like an open building, an insulated building, or during the construction process. Projects I've had to worry about it on have been community centers where there were arenas and swimming pools in the same building, because it can have a big impact. Or buildings where you have gyms that can turn into an arena. Now, most arenas, the slab for ice is really, really good. I remember playing hockey in the Ricoh Center and at the new version of the Maple Leaf Gardens. And the lights are so hot on the ice that you can actually feel when you're skating under the lights. Like it's you'd have to really plan your gear when you were playing on those ice surfaces. But then I also remember playing at York University in their rink, and it being so cold that your feet would freeze. So different rinks can have different kind of air makeups depending on how they're being used. A good story about this, and so it wasn't a project I was involved on. It's a story I've heard kind of secondhand. There was a project. Well, actually, there's two good stories. So one is there was a building. It was built, so the steel's exposed. It's not insulated yet. The cladding isn't on it yet. The cladding's going on, and the windows needed to be installed. So they came, and this is the standard way projects are built. They came and they measured the windows openings, went and made their windows, and they came back like a month or two later and tried to install the windows, and they didn't fit. They're like, these windows don't fit. Everyone was freaking out, as you can imagine. So the steel fabricator the next day spent the whole morning measuring all the window openings, looking at the window shop drawings and saying, these are identical, like within a millimeter of each other. There's no way these don't fit. So the window guys came back that afternoon and again tried to install the windows, but they didn't fit. After a bit of back and forth, it was figured out that the measurements were taken in the winter, and then they were being installed in the spring. And so in the morning, the building was in shade, and that's when they confirmed the measurements. But in the afternoon, it was in full sun. And you know those spring days where it can be -5 in the morning and 15 degrees in the afternoon. In the full sun, it can even feel like 20 or 25 sometimes. And so the steel was contracted in the morning and when they took the original measurements in the winter. And then by afternoon, the steel was expanding, so the windows didn't fit anymore. They were too small for the windows. All it took was coordinating that, making sure that everything was adjusted, and then accounting for it when the building was enclosed. So a lot of that is means and methods. It's under the contractor's scope. But for projects that could have that over a life cycle, we need to understand how that behaves. Another construction story, so often when they install steel, the crane is the most expensive thing. So they will crane the piece of steel in and then put like a small bolt or two in, and then come back later and install all the rest of the bolts. And it's under construction loads. There's no flooring on it. The loads are nominal. So this one was a particular building that was on 2 concrete walls with a steel beam on it. So it got erected into place, just quickly had bolts put into it. Everybody went home at the end of the day. They came back and the steel beam was sitting on the ground. And so what had happened was it had been installed in the afternoon in the sun, spring or fall. It got cold, the steel contracted. It now was too short to sit on those walls. Now, we're talking like a really small amount, just enough to slip it off, but it wasn't held in place by the bolts that would have been designed to take that load and hold it into place. So that's where the design of this becomes really important, because we can make it stay in place. It just has to be designed for it, and it probably was. But the bolts weren't there. And so it contracted the amount it needed to contract to slip out of the supports and fall down to the ground. Prestress. Prestress isn't one we're going to talk about a lot, but prestress, do I have an elastic? I always have an elastic. So prestress is basically saying we can't put any compression on this, right? It's an elastic. If I try to push on this, I have no ability to resist that load. But if I stretch this and push on it, I release some of the tension, but I don't put it into compression. I just release some of the tension that I previously put on it. That is prestress. So if I had this as some weird type of column that I stretched up, so there's something holding it up, but then if pressure got put on it to compress it, it doesn't go slack. And so I can do that all the way to here, but if I do more than that, then it goes slack. That's the principle behind prestress. And so this is a prestressed saw. If anyone's ever tried to saw before you pre-stress it, it doesn't work. That bow will buckle. What you do here is it's a loose fit, and then this clasp, as you clasp it shut, pulls it taut. Vibration is another load that we worry about. Most buildings are massive enough that vibration isn't a concern. The times it can be concern are usually on light, whippy steel structures. This tends to be what I think of when I talk about vibration. One of the things that we really are concerned about vibration on is feature stairs. Normally there's very little material on them to help deal with that vibration, and people are very sensitive to the movement. So we have continuous vibrations, which are a steady repeating load. Like I've told you before, humans often move at about 2.5 hertz, and I kind of gave you guys a little demonstration early in the term about that. We have damping, which is often helped with by mass of building or the friction within things. And the example I talked about at the beginning of the term was the Olympic weightlifting floor in the Goldring Center for High Performance Sports, where what we ultimately did was isolate the floor from the rest of the building. I don't think I drew it. I'm going to draw it for you guys just because it's a fun thing on how we isolated that. So what we had was up here on this floor. So these were all of our trusses, drawn poorly, I apologize. So up here we had, you guys can't see that. Give me just a sec. Okay, up here we had an MRI. Right here we had an Olympic weightlifting floor. These floors are hung from this floor. This is very sensitive to vibration. This causes a lot of vibration. So you can imagine you throw this down, this vibrates, it vibrates up these and impacts the MRI right here. So what we did for this floor here, most of our floor was hollow core slab on steel beams. What we did in the zone of the Olympic weightlifting floor, because we wanted this to be a flush floor, we wanted it not to look like there was any difference between it. What we did was we put in this very big, massive, solid, precast chunk of concrete. So these were all, I believe, 250 or 300 hollow core. This was 500 solid concrete. We put a piece of bond break here and put hydraulic jacks in a grid of 1 meter by 1 meter, and then cast another concrete slab. So this was precast. This was cast in place. We poured it 25 millimeters too low, and then we engaged all the hydraulic jacks to lift this up 25 millimeters. All of these had isolation dampers inside of them. So now, if the Olympic weightlifting weights were thrown on this floor, this was massive to help dampen it. These were isolators, which took out most of the weight. This was massive and disconnected to this only through a steel connection. So very little of the weight got transferred out to these elements. And so I've drawn this poorly. This person wouldn't have been right under the column. It would have been more like right here was where our Olympic weightlifting floor would have been. And I gave a tour once while they were using this floor, and I had a person stand right here and a person stand right here. These people could not feel the vibration. These people said that they felt it so strongly. It was almost unnerving. Okay. We do check to make sure our buildings don't have resonance that would allow for amplification. So that means we try to make sure our buildings do not have the same natural frequency as exterior stimulation. So that would be, for example, the continuous vibration of people could cause amplification. Wind, and the natural frequencies of other things that could be going on, mechanical units and things like that. Okay, so we've talked about all of the loads. Now what we need to talk about is factors. How do we factor up our load? We're pretty sure we know exactly what the maximum load our building could see is for dead loads and live loads and snow loads and wind loads and seismic loads. But what if we're wrong? What if we should build in just a little bit extra? Now, how do you pick how much? If you wanted, you could pick 10 times as much. But the building becomes really expensive to build that. Hey, Flash, what are you doing? 3 is such a lovely age. So what if we're wrong though? And so we could pick 10 times if we wanted, but then we're designing something 10 times more what we think we need to. You could do it, but nobody could afford to build that building. So codes or all kinds of statisticians in each country have come up with the load factors for their country. Now, I'm going to say that they're pretty much the same all around the world. The reason the factors might look different is because they applied their loads differently. So, for example, in Canada, our single person load is 1 kilonewton for a guard or a particular structure. And in the US, it's 1.33. We use a load factor of 1.5. They use a load factor of 1.4. So it all ends up being about the same load, no matter where you talk about it in the world, but the process might look a little bit different. I have to pick one to teach you with, so we're going to pick the one that's applied where our school is. I know some of you might not be here right now, but this is where we're picking to do it. So we are going to be following the National Building Code of Canada, following Part 4. All that to say, I have given you all of the things you need in PDFs posted to Quarkus for this. So remember back in the day, what they used to do is add up all of the loads. So me sitting on that table, they'd add up me and the table and anything else that could be seen on it, and then pick some factor of safety and make sure that was less than the capacity. And the capacity was the capacity. We said that doesn't really account for the fact that different loads might need a different safety factor. And what if we got the capacity wrong? Some of that should be built into the capacity, or our careful factor should be built into the capacity. So what we do now is we factor up the loads, we reduce the capacity, and make sure that factored load is less than the reduced capacity, or our factored load is less than our reduced capacity. Next term, we're going to look at this symbol a lot for the different materials. I pretty much only draw this symbol once, and it's today. And actually, I don't even draw it. I show it to you in a chart in about 2 minutes. So we factor the load and make sure it's less than the reduced capacity. This term, we're going to spend all of our time figuring out what the factored loads are on our members. And next term, we're going to figure out what the reduced capacities are. That means the 2 courses are like one continuous course. We have to know how to do this part next term, because what we're going to try to prove is the factored load is less than the reduced capacity. And one time had somebody complain that they didn't think it was fair that they had to know structures 1 to do structures 2. So I like to just reiterate that yes, you have to know structures 1 to do structures 2. It's one continuous knowledge stream. It can't be, I've broken it up into material sections or data sections, but it is a progression of knowledge. So the subscript F means that we factored that load. So it just means if we're talking, you can see at a glance that it has in fact been factored. And I do this all of the time in my design sheets. I wonder if I have any open. Let me just open one of my design notes. This one's not the best. This one, I often will show factored, unfactored, and then factored, but you can see here VF and MF. I'm telling myself I have in fact included that factor in this. And the reason that's important is if I came back later, there are certain things where we don't include that load factor, and that is our serviceability stuff. Remember all of our damaged finishes and human comfort and all of that stuff? Well, for those, we don't have the factor applied. And that's why it's important to know what we're talking about. The shorthand for most people is to use this F to say that we're talking about the factored load. The subscript R means that we've talked about the reduced capacity. This reduction factor has been applied to the material. This whole method of design is called limit states design. Now, we have ultimate limit states, which is our factored life safety strength issue. We also have another subset that's called serviceability limit states, and that's our stiffness stuff. Remember, strength, stiffness, stability. Stability, next week we're going to talk about drawings, and we'll know how to satisfy our stability requirement. Today, we're talking about the load factors that we use for strength and the factors we would use for stiffness or our deflection or our serviceability limit states. So, limit state design. Ultimate limit states, or ULS, is talking about strength. Serviceability limit states, SLS, is talking about serviceability. In the code, the National Building Code of Canada, you get this chart. Last year I had somebody say to me, this chart is different than what I found on the internet. Well, it's different because of, I had two different people send me charts. One was looking at an American chart, so their load factors are completely different. I said that they figure out their loads slightly differently, and then they figure out their factors slightly differently. It works out to be about pretty darn close to the same factored load. But they adopted it in 2015 in the National Building Code, but provincially they didn't adopt it until around 2020. They changed some of these factors. So we have a principal load case. So these are our load combinations for our principal loads. D is our dead load. So load case 1 is 1.4 times our dead load with nothing else. It's all by itself. Then we have our next load combination, which is 1.25 times our dead load. We'll come back to the 0.9 times dead load, plus 1.5 times the live load. But then look over here. It also says we have to include 1.5 times, or 1 times the snow load, or 0.4 times the wind load. So these are actually 2 load combinations. Possibly possibly 4 load combinations if we think about this 0.9 dead as well. But this one line is capturing multiple load combinations. See this 1 times snow load? A few years ago, that was only 0.5. So all of the work that I had done for teaching this course was updated last year after we implemented this in the Ontario Building Code. So I think even last year there was still 1 or 2 small mistakes that I had found where I hadn't updated everything accordingly. But I think we've gotten everything now. The TAs have looked at everything. So hopefully we've captured all of those changes. All right, the next line is 1.25 times the dead load, with snow as the principal load. So dead and snow are the important ones. And then we have companion loads of either live load or of wind load. And then we have a load combination of dead and wind load with a companion load of either live or snow. And then we have a load combination of dead and earthquake with either live or snow. Oh no, live plus snow. So this one we would add those all up. All right, let's talk about the 0.9 dead. Why would we ever use 0.9 dead? It reduces the dead load. Remember, what we want to do is make sure our factored load is less than our reduced capacity. That makes sense that we would always assume it could be higher, right? Well, what if we had, I'll pull out my elastic again. What if we had this elastic that had a dead load pulling down on it, okay? So we have a dead load pulling down on it, and then we have something, a spring or somebody pushing up on it. Those 2 loads are acting in opposite directions. How do we figure out what the worst case load is? Well, the dead load pulling down on it, 1.25 times dead, and nothing pushing up. That seems to make sense. But with the pushing up, we would assume that it could be 1.5. But the weight down, we want to see what's the most it could be pushed up the other way. Well, for that, we would assume 0.9 dead. Where do we see this? Let me pull out our braced frame here. Okay, we have our braced frame here. We have dead load pushing down on this column and this column, all right? Wind load pushes this in this direction. So if this was on the ground, this wants to tip over. This column is pushing down, so we've got dead load pushing down and wind load pushing down. On this side, we have wind load trying to pull the column up and dead load trying to push it down. Well, with no wind on it and dead pushing down, that's the worst case for that column for the downward load. But if the wind was pulling up, what if it was enough to be more than the dead load pushing down? We need to check both versions. So we would assume less dead load. We would make our calculation assume that we guessed too much dead load because our dead load is helping hold that side down. And so for some things, we have to think about both scenarios. And we're going to do some examples, so don't worry about it. And even for these examples, I've included Excel sheets, and you're going to do an example in the assignment where you have a version with some uplift in one of the load cases. All right, so let's see. So this was this chart. The other thing a student said to me last year was, this chart seems to be missing a lot of the load combinations. It's a small chart, but there's a lot embedded in it. What this chart is actually saying is this. We've got, and so this is a naming convention I came up with to help keep track of things because I build models. That's one of the things that's my expertise, is building really complicated models, but I needed to be able to keep track of my load combinations. So I came up with this naming system. I've since seen other people using it. Some have copied it from me, some have come up with it on their own, which means that this is kind of a pretty obvious naming system, which means you can name them whatever you want. You're going to find it handy to use this naming convention though. So this U means I'm talking about an ultimate limit states load combination. Ultimate limit states, dead. Well, that's my 1.4 dead load. That was that first one in that chart. Ultimate limit states dead and live is just my 1.25 dead plus my 1.5 live. But I also had the version where I needed to add my snow and I needed to add my wind. So my 1.25 dead plus my live plus my snow, my dead plus my live plus my wind. Well, then there was the version where my snow was the principal companion or my principal load. And then there was snow with my principal as my principal load with companion load, different companion loads. And this is it with wind as the principal load, and then wind with the principal load and companion loads. So we actually have quite a few more load combinations here. Then we need to think about wind as the principal load, but dead and wind acting in opposite directions. So our dead load pushing down and our wind load pushing up on this column. So for that, we would have 0.25 dead and 1.4 wind load. Would live load just mean we would have less tension on this column? Yeah. We could add the other load case with live pushing down, but we want to figure out what's the least amount of load pushing down while we simultaneously have the most amount of load pulling up, because we need to make sure we look at the envelope. We need to look at the worst case of compression and the worst case of tension. And then we have our earthquake loads, so just dead and quake on their own, and dead and quake with live or snow. The reason we don't always just do live and snow is the same reason. What if the quake load was pushing this way? Live and snow would be counteracting the quake load. So we need to look at both ends of that spectrum. We need to look at just dead and quake, and we need to look at dead, quake, live, and snow to look at the both extremes. Okay, so this says wind. Look, I said wind XP. That shouldn't have been there in this one. It just says wind for the most part, but I have a building. Wind could go in this direction. Wind could go in that direction. But wait a second, my building has two directions. Wind could also go in this direction, and wind could also go in this direction. I have 4 wind cases. So that means anywhere that had a wind combination in here needed to have 3 more combinations. All right. And then what about quake? Quake could, we don't know what way Dave is pulling that yellow mat. He could have pulled it in any direction. So we need to think about quake in all of those directions. So this simple list turns into this. So we've got even more load combinations. This is all still from that one little chart that only had a few lines of load combinations. But this is how many we need to apply. But wait, do you remember our wind loads had end zones? So if this was our building and the wind was going in that direction, we needed to think with an end zone here and an end zone here. If the wind was going this way, end zone here and end zone here. So we actually have to double all of our wind load combinations. Earthquake, we have torsion that we worry about, which is essentially what our wind zone, our end zone is doing in wind. And that's very clearly stated in the building code. We say, if this is our roof and we think the center of our roof is right here, our center of mass is right there, we say, wait, it could be 10% to either side. And so we build that eccentricity into our roof, which means we actually have even more combinations. I don't think I add another slide. So that's almost 40 combinations, but that's still not enough because we have our end zones and our earthquake torsion. I've done a project where they did a wind study, where they actually looked at the wind in different patterns on the building. I did a snow study project that had 12 different snow combinations on the roof. So for everywhere that I had a snow load, I needed actually 12 versions of that. That particular project had over 1,200 load combinations. So you can see why having a computer program becomes very helpful, because I needed to apply those 1,200 load combinations to every single element in the project. So tracking that becomes very important. I often say that this lecture that we're about to do is basically about accounting. You need to keep track of all of your lines of data and pull out what the worst one is. Imagine if you were doing a projection for a business. You want to look at, assuming you did the most business you could have possibly done each month, and your costs were the lowest you possibly could have had each month. All right? And that's going to be your highest profit you could see. But you also want to look at the version where you could have made the least amount of money every month and somehow your costs were the highest you could have seen every month. And that would be your lowest profit you could see. It could even be in the negative. Checking your highest profit with your highest costs doesn't really, your highest income with your highest costs is going to be somewhere in between those. What we really care about is those boundaries, or those two extremes. We can check the ones in the middle as well, and we do, but the extremes are what we care about because that's our envelope. Now, we're going to talk more about that. We're going to do some examples of that. So don't worry. I know this chart is intimidating. Excel is your friend for this assignment. All right, so that's just our strength. Remember, we have strength, stiffness, stability. Stability, we draw drawings. Strength, we have to apply all those load combinations. And yes, still do more work. That's going to come. We need to think about axial loads and shear loads and moments. But then we also have stiffness, and stiffness is tied to our serviceability. So serviceability limit states, you guys looked at what the serviceability criteria were at the beginning of the term, and we don't really know how to connect these two things yet, but we know those limits need to be maintained. And so we're going to have some loads that cause actual movement. The actual movement we'll talk about next term, but the loads that cause it are the serviceability limit states load combinations. So these calculations use the importance factor for serviceability. Remember the importance factor for snow and wind in a normal building was 1, but for snow, for serviceability, it was 0.9, and for wind, it was 0.75. Well, these serviceability limit states are using those serviceability importance factors. Remember, I got you to track your ultimate limit states and your serviceability limit states, and you didn't really know what the heck I was talking about. Well, this is what I'm talking about. So it's 1 times snow, but this snow has our 0.9 built into it. So for a roof, we would be worried about serviceability dead and snow, which is our dead plus snow, or a serviceability snow. Remember, we had deflection criteria for dead and snow together or snow by itself. Well, that's why we track multiple things here. These ones, we are not looking for the highest load between these two. because we're comparing them to different data. Floors would be dead and live or live by itself. Foundations would be dead and live or dead plus snow, and building movement would be wind and quake. But don't worry about this too much. We're going to keep the serviceability limit state stuff really simple. We're going to be talking about dead and snow or dead and live for the most part. So I am making today's examples for the ultimate limit state stuff the most complicated you're ever going to do in my course. After this, it's going to get very, very, very simple. You're only going to have 2 loads, maybe 3 tops. Whereas today we are going to do an example, and you in the assignment are going to do one with dead, live, snow, wind, and quake. And you're going to keep track of that in an Excel sheet. Okay, load combination example 1. What is the factored compression and tension loads on a column that can have 12 kilonewtons of compression, 10 kilonewtons of compression, 5 kilonewtons of compression for snow, and wind 10 kilonewtons of compression or tension? So that's saying we've got this. This column here could have 10 kilonewtons of dead, 10 kilonewtons of live, 5 kilonewtons of snow, 10 kilonewtons of wind, or 10 kilonewtons of wind. So we need to think about what that means for this column. We want to look at the worst case compressive load, and if it exists, the worst case tension load. Okay, so let's do this example. All cool with the kids in there?
Yep, for now.
The kids have been home together for 3 days now, pretty much in isolation, meaning as much as they love each other, they are on the verge of being at each other's throats, which means everyone is on the verge of being at everybody's throats. Okay, I'm going to take a drink of water. Okay, hey, just to show you my kids do love each other, I'm going to share a drawing, just because I'm a proud mom. This is a drawing my 5-year-old drew. He drew himself and his 3-year-old brother. When I asked him what it meant, he said, "Mommy, this is me and Duncan, and we're asleep, and we're sharing our dreams." So, you know what? Good kids, I think, but right now, everyone's a little on edge. Okay, let's look at our example. All right, let's take a look. I've told you the best thing to do is keep track of your accounting. So I'm going to draw, I always like to draw a little picture. Let's draw this column right here. We don't really know what any of this means yet. I'm going to draw my free body diagram. You have no idea what a free body diagram is yet, so do not fret, do not worry. We are going to learn this soon enough. Let's see if I can get this down just a little bit more. Okay. That said, we could have 12 kilonewtons of dead. It said we could have 10 kilonewtons of live. It said we could have 5 kilonewtons of snow. It said we could have 10 kilonewtons of wind, or we could have 10 kilonewtons of wind. So there's a condition where our wind could be trying to pull this column upwards. Okay, and so we need to figure out what the worst case loads are on this. We want to know our worst case factored compression load and our worst case factored tension load. So compression we'll often talk about as a C. We want to know CF, and we want to know TF, which is our worst case tension load. Now, there could be other values in between here. We don't care. We're going to design for the worst. We could design for somewhere in between here, but what's the point if we could see something more than that and fail our column? We want to design for our worst case loads. So let's take a look at what those are. Ultimate dead. All right. 1.4 times our dead load, which was 12 kilonewtons. I'm going to write these all in, and then we'll go back and calculate them all. Ultimate dead live, 1.25 times 12 plus 1.5 times 10. I think you can tell right away that this one's not going to be the worst case because it doesn't have the companion loads added in. But I find it a good process to check them anyway. Once you get good at it and you know what's obviously not going to govern, you don't have to do it. But for now, let's try doing them because sometimes it's not as obvious and it's good to have a process in place. Okay, let's look at ultimate dead with just snow. 1.25 times 12 plus our 1.5 times our snow, which was 5. Ultimate dead wind. I'm going to look at all of my downward loads first. 1.25 times 12 plus 1.4 times 10 for our wind. Okay, now I am going to look at companion loads. So ultimate, dead, live, and there's two different live with companion loads. There's live with snow, and there was live with wind. So live as the principal load, and snow or wind as the companion load. So 1.25 times dead, 1.25 times dead, that's the same, plus our 1.5 times our 10, plus our 1.5 times our 10 for our live load. And then we have our companion loads. This one could be 1 times our snow, which was 5, or 0.4 times our wind, which was 10. Now we need to do it with snow as our principal load and either live or wind as our companion load. Okay, so we have 1.25 times 12, 1.25 times 12, plus 1.5 times 5 for our snow, plus our companion loads. 1 times our live load, which is 10, or 0.4 times our wind load, which is 10. These are all acting downwards. These are all the cases where I'm using these ones acting downwards. Then we have the case where wind is the principal load, and either live or snow is our companion load. So 1.25 times 12 plus 1.4 times our 10 plus our companion load for wind, for live, and our companion load for snow. So for this, it's only 0.5 for either of these, not our 1. And for live, it's 10, and for snow, it's 5. So that's all of our combinations acting downward. Now, if our wind is acting upwards, we know that the dead load can't disappear. The dead load is there. That stays. It's part of our building. But that wind upward could happen when there's no live, no snow, and obviously there wouldn't be wind acting downward simultaneously. So we could check wind acting upwards while all of these are acting downwards, but that's not going to show us the worst case uplift. The worst case uplift is going to be when all of the upward loads are there and as few of the downward loads are there. So this is going to be, and I always put a little U here to remind myself I'm talking about uplift, dead, wind. Again, I could do uplift, dead, live, snow, but those don't have any upward forces, so they'd be 0. I could do upward, dead, wind with my live load, but that would give me a smaller upward value. So this is where I have an upward load here. What if, so we can't remove our dead load, but what if we got our dead load wrong and we had less than we thought? That would give us the worst case upward force. So 0.9 times 12 plus 1.4 times 10. If you want, build a spreadsheet and take a look at all of these. And so actually, sorry, not plus, minus. This one's acting downwards. This one's acting upwards. So that needs to be a negative. All of these are acting downwards. They're all acting in the same direction. This is not. It's acting in the opposite direction. So let's plug some of these into our calculator. 1.4 times 12. 16.8 kilonewtons. 1.25 times 12 plus 1.5 times 10 equals 30 kilonewtons. So we already know that one's not our worst case one. Let's see if we can get that a little bit, the light a little bit better for you there. As the sun is coming out, my paper is getting really reflective. Okay, 1.25 times 12 plus 1.5 times 10. Oh, times 5. All right, so that's 22.5 kilonewtons. Well, that one's not the worst case. We still got 30 as the worst case. All right, 1.25 times 12 plus 1.4 times 10. 29 kilonewtons. Well, that one's not the worst case either. Okay, 1.25 times 1.5 times 10 plus 1 times 5. Oh, 1.25 times 12 plus 1.5 times 10 plus 1 times 5 gives us 35. Remember, we have to design this to work for all of these, but if we're going to pick a value to ensure is less than our reduced capacity, might as well be the highest one. So we might as well just start talking about this 35 kilonewtons. If it works for 35 kilonewtons, it works for 30 kilonewtons. Okay, let's check our next one. 1.25 times 12 plus 1.5 times 10 plus 0.4 times 10 equals 34 kilonewtons. Well, it's not that one. We've got 1.25 times 12 plus 1.5 times 5 plus 1 times 10. 32.5 kilonewtons. It's not that one. 1.25 times 12 plus 1.5 times 5 plus 0.4 times 10 is 26.5 kilonewtons. It's not that one. I'm just going to start writing these in because I've already calculated them previously. That one's going to be 34. It's not going to govern. And this is 31.5 kilonewtons. So it doesn't govern. That tells us that our worst case compressive load is this one right here, our 35 kilonewtons. We also need to worry about our worst case tension load. I'm going to show you one in just a minute where we can still take a look at this. I'll show you why I'm only bothering calculating one. 0.9 times 12 minus 1.4 times 10 equals minus 3.2 kilonewtons. So this load's acting down and that load is acting up. What if, just for fun, I checked ultimate uplift dead live wind? So 0.9, actually, what if I did 1.25 times my 12 plus my 1.5 times 10 minus my 1.4 times 10. Or sorry, it would be 0.4 times 10. 1.25 times 12 plus 1.5 times 10 minus 0.4 times 10. It's 26. I know that this is the worst case one. These ones weren't as obvious because I had two values worth 10. Like, it wasn't going to jump out to me because look at even how close these two were to each other. But for the uplift version, we know anything acting downward is just going to lower our value. So this just isn't worth bothering to check. So these are our worst case. CF equals 35 kilonewtons and TF equals 3.2 kilonewtons. So this is acting down and that is acting upwards. So this column, I'm gigantic. Okay, make me smaller. If the wind is blowing like this column here, we're in a normal building without the wind blowing. Our worst case load for our column is our dead live snow case. So this column right here could see the maximum compressive load of 35 kilonewtons. So we take the people off, the snow comes off, we've still got our dead load, but our wind is trying to lift that column up. It's trying to pull up because it's trying to tip it over, just like that. I actually broke this. And so we want to look at this with assumptions that we maybe overestimated our dead load because we need to design this to not pull apart. This brace needs to be designed for that tensile load too, so that doesn't happen. They build them better than plastic toys. Okay, so here is that all worked out for you as well. Okay, we're gonna do another example because I know some of you already have this. You've got it, you figured it out, and you're like, this is the easiest thing ever, Shannon. But I know for some of you, this is a really hard one to process. The uplift thing seems to throw people off. I will admit, tracking these things is a pain in the butt. I make mistakes with it. This is why I suggest you use Excel, and I suggest you talk to each other because this one you should really be communicating. Don't rush and try to do it all on your own. Talk to each other and try to make sure you haven't made a typo because it's really easy to do. It is why I will often, even when I'm building my complicated models, I'm going to open, in the background, I'm going to open one of my models here just to show you. When I'm building my models, I will often do a hand check to make sure I haven't screwed up entering things into my modeling program, for example. It's just taking its time here. Sorry, I'm going to close this. I'm going to close this. Okay, just because we were talking about it, here's the design software I happen to use. Let me pull up. This is a good project to pull up. So this is a project in California. Let's take a look at my load cases here. So you can it shows up on a different page, obviously, of course. It's a little bit hard to see, but I've got my self-weight of dead, my superimposed dead, live. I've got quake in 4 directions. I've got wind in 4 directions, but also incorporating torsion. And then in my load combinations, I incorporate torsion for my earthquake. So here are my load combinations. Okay, so take a look at this. You can see that I've built these in. And if I open up any one of these, you can see that I am building these things in. In this one, I needed to worry about it as a downward load, but then I also needed to worry about it as an upward load. This building wouldn't have snow or live on the roof. It's snow, no snow in California in this particular region, and there's no live load on this roof. So I needed to look at the, so here's that same combination. that same combination, but the uplift version of it. So I had it acting the worst case for both things. Now this is a lateral load, so it's how it's being applied. Okay, so I just wanted to show you what's happening in models, that I actually do all of these things I'm telling you that we do. These are not abstract things. These are things that engineers do every day when they set up every project. So this is a real process that we're thinking about. So you saw that my building that I was doing was this complicated little gem, but we're gonna go with a very basic, simple one here. So we've got an office building that's got a pretty regular bay. We've got purlins along here, major beams along these grid lines, and columns at all of the grid intersections. So here's a plan of it. These are all purlins along these lines. So in between A and G, all of these beams running in this direction are purlins. All of our major beams along grid lines 1, 2, 3, 4, and 5 are beams. We've got columns on all our major grid lines. Does it show our bay sizes here? Yeah, so we're a 7 by 8 grid. So we've got all the information we need. We've got the height of our building. All right, determine the ULS and SLS load on the roof in KPA using the dead and snow loads we calculated last week. So these were already done last week. We knew where our building was located, and we looked at the roof assemblies and floor assemblies throughout our building. So ULS and SLS for the roof. Determine the ULS and SLS on level 2, 3, and 4 in KPA using the dead and live loads calculated last week. What is the total load on column 1 and column 3? So an Excel file for the columns in this example has also been uploaded. I'm going to go through some of it by hand, but the majority of it we're going to reference the Excel file that I have uploaded for you, so it is there for you to take a look at, so you can see what's embedded in it as well. What's interesting about this, and the reason I have us look at the ultimate limit states loads on the floor, is rarely are beams governed by live load reduction factor. They have a small tributary area. So often we don't have a live load reduction factor for them. Sometimes we do, but it's rare that beams themselves would be governed by a live load reduction factor. Columns, however, as they go down the building, pick up an increasingly large area, meaning we can apply a live load reduction factor. I am going to tell you that you will have one question on the exam about live load reduction factor, and you're going to have it in this, but we are not going to bother much with live load reduction factors after that. Check on your project. I can't remember if the areas are big enough for a live load reduction factor or not, but next term, we're not really going to spend any time talking about live load reduction factors. It's important that you know they exist because they can play a big part in designing elements, but it's still not that common to have it govern. Okay. All right. Well, let's see. Actually, no, most of this... Okay. I'm going to... point us downwards here. And so we're just going to go through some of this right now. Actually, it might just be easier. To do it this way. I usually like to do the hand calculations because it slows the process down. It's really easy to talk too fast if the calculations are done. When I first set all of this up, it was in the old building and there was no means to show hand calculations, and the touch screen they gave us was just too hard to show information. So I thought I was being smart and did it all ahead of time in PDF or embedded it in the presentation. But obviously people found it went too fast. So I'm going to try to talk slow and do it as if I was writing out the hand calculations, because when you're writing it out, it's a lot easier to talk about it. If you are struggling with any of this, I suggest you take the time to do it as a hand calculation. So last week, we calculated the roof loads. We figured out that the dead load was 1.32 kPa. So we looked at what the dead load assembly was and figured out the dead load on the roof. We knew where the building was located, so we were able to calculate what the snow load was. And we calculated two, the ultimate limit states and the serviceability limit states. We know that this means that 0.9 importance factor is embedded in it because we're talking about serviceability. So for the roof, the ultimate limit states factored loads for strength. So remember, these are all of our factored loads for strength. We only have dead and snow, nothing that could cause uplift. So dead, we have to look at dead load by itself, which is 1.4 times our dead load, gives us 1.85 kPa. We need to talk about the ultimate dead and snow case. So 1.25 times our dead load plus 1.5 times our snow load is 3.33 kPa. Was there any live load on the roof? No, we don't need to worry about that. So the worst case load for strength design of the roof is 3.33 kPa. Serviceability is not about the worst case. We will end up tracking it against different data. And you're thinking, why are you making us do this if we're not going to use it right now? It's because right now we're talking about it and it's fresh in your mind. If you get in the habit of tracking it, next term when we need that information, you'll understand the process. Okay, so serviceability limit states factored loads for serviceability or deflection. So we have two things. We need to look at dead and snow together and snow all by itself. So dead and snow is just the 1.32 plus the snow load, but it was the snow load that had the importance factor for snow load for serviceability built in. So our 1.1. And then snow load all by itself. We are not looking at a worst case for serviceability. These will be compared to two different criteria at a later date. Remember that we had dead and snow together, had a length divided by 240, and snow load by itself would compare to either length divided by 360 or length divided by 300, depending on what the finishes were. Our floor loads were the same for every floor in the building, and we looked at what the dead load assembly was, and we calculated that it was 2.85 kPa. The live load for an office building is 2.4 kPa. On each of those floors, we don't have snow. They haven't told us anything about wind, and they haven't told us anything about earthquake. You are going to do an example in the assignment that is very similar to the last example, where it's a smaller problem, but you have all of the load types. So you're going to do both sort of things. I'm going to make you do an easy example with lots of load cases and a harder example with less load cases to try to work through the whole problem. I'm not going to give you a complicated problem with lots of load cases. So we have our floor loads, and so we need to look at dead by itself, and we need to look at dead and live together. So 1.4 times 2.85 gives us 3.99 kPa, or 1.25 times our dead load plus 1.5 times our live load gives us 7.16 kPa. That is very much a typo here, so I will fix that typo. That should obviously be 7.16, and 7.16 is what's used in the example. So slide 24, worst floor. So you should be seeing 7.16 kPa as the worst case load. We can take the worst case here because we need to design this for the worst case. Serviceability, we have two different criteria. We have dead and live together or live by itself. There's no worst case because these will be compared to two different criteria at a later date. And by later date, I mean middle of structures 2. We will use this information, I promise. I'm not making you track it in vain, but we don't have the knowledge yet to make use of it. Okay, so column C1 was the very first column we needed to look at. So column C, so this is grid line A, B, C, and this is grid line 1. So we're talking about this column right here. We need to figure out what the tributary area is. That's the very first thing we need to do. So we know that it's picking up half of this bay and half of this bay added up to make that tributary, and half of this bay. So 7 meters times 4 meters is our tributary area. So you can see our tributary area is right here. So let's take a look. 7 times 4 is 28. So you can see that all calculated here. Why did we calculate the total factored loads on the floor if we don't use it when we're looking at the columns individually? Because look here, we write out what the actual loads are on each floor. I wonder if it's worth... Do I have these worked out by hand? I don't. I wonder if it's worth doing it anyway. What I don't want to do is start something that is gonna screw you up when it's all embedded here in the Excel file. Okay, let's go for it. We're gonna take a look at it here. Okay, so we have a column that is 4 stories high. And then here's the ground. All right, so it's not picking up the ground. This is the roof. This is level 2. This is level 3. And this is level 4. So this portion of the column is we're calling it level 4 to the roof. This portion is level 3 to level 4. This is level 2 to level 3. And this is ground to level 2. We need to figure out what the worst case load is at every portion of this column. This has dead and snow on it. This has dead and live on it. This has dead and live on the floor, and this has dead and live on the floor. But this column only has dead and snow. This column has dead and live and snow. This column has dead and live and snow, and this column has dead and live and snow. In fact, this column is picking up the snow from the roof, the dead from the roof, the live from the fourth and the dead from the fourth, the live from the third and the dead from the third, the live from the second and the dead from the second. So this column is going to have the most load on it. The impact of snow load on it kind of decreases as it goes down. As this increases, we're picking up more and more live load area as well. Okay, so let's take a look at what's happening for this column. So let's take a look at the column from level 4 to roof. I'm going to open my Excel file so I have access to it while we're talking as well. Okay. So we have a dead load of 1.32 kPa and a snow load. We're just going to talk about, let's see, what did the question actually ask us here? It's important to know exactly what it asked us. So it said, what is the total load? That should say factored. Total factored load on columns C1 and C3. So I'm going to fix that too. Slide 23. Factored. All right. So we're not going to worry about serviceability loads right now. Let's just focus on this hard part. Okay, so we've got our dead load and our snow load. So, and we know that our tributary area is 7 meters by 4 meters, or 28 meters squared. Our ultimate, well, let's actually figure this out one at a time. Our dead load is going to be 28 times 1.32, and our snow load is going to be 128 times 1.12. So every square meter of this roof is supporting 1.32 kilonewtons, and we've got 28 square meters. So we've got 28 times 1.32, or 36.96 kilonewtons. And we've got 28 times 1.12, or 31.36 kilonewtons of snow load. Ultimate dead is 1.4 times 36.96. Ultimate dead snow is 1.25 times 36.96 plus 1.5 times 31.36. Okay, 1.25 times 36.96 plus 1.5 times 31.36. We get 93.24 kilonewtons. I forgot to calculate this. 1.4 times 36.96 equals 51.74 kilonewtons. What's the worst case factored load on our column from level 4 to roof? Well, CF from level 4 to roof equals 93.24 kilonewtons. So that's easy. We've got our first portion of this done. Let's take a look at the column from level 3 to level 4. From level 3 to level 4, it's supporting the dead and live from level 4 and the dead and snow from the roof. So it's this portion of the column here. It's picking up this dead and live and this dead and snow. So dead load roof equals 1.32 kPa and a tributary area of 28 meters squared. The tributary area was the same on all the floors. They don't have to be. They could have different tributary areas. So our P dead is 36.96 kilonewtons. I'm going to start to streamline how I calculate this. Our snow load roof is 1.12 kPa, and our tributary area is 28 meters squared. So our P snow is 31.36 kilonewtons. Our dead load level 4 is, what is our dead load for the floor? 2.85. Remember we calculated that last week. And our tributary area is still 28 meters squared. Remember this, at this floor we could have a different tributary area. So our live load is 2.85, our dead load is 2.85 times 28, or 79.8 kilonewtons. And our live load for level 4 is 2.4 kPa with a tributary area of 28 meters squared. So don't yell at me yet. I will talk about the live load reduction factor, but hold on. All right, so 2.4 times 28 equals 67.2 kilonewtons. Let's talk about the live load reduction factor. So our live load reduction factor for this type of loading, our live load reduction factor is 0.3 plus the square root of 9.8 divided by our tributary area. Okay, our tributary area for this region of the column is only, this is all of the area that's supporting live load. So this is tributary area of live load. We have 28 meters squared. So 0.3 plus the square root of 9.8 divided by 28 equals 0.3 plus the square root of 9.8 divided by 28 equals 0.8916. Okay, so we've got a live load reduction factor that we can apply to this live load. Let's take a look at our different load combinations. I'm not going to stop and do dead and snow by itself and dead and live by itself. That's in the Excel sheet. I'm going to do it with the companion loads right in. So we're going to have ultimate dead, we're going to have ultimate dead, live as the principal, snow as the companion, and ultimate dead, snow as the principal, live as the companion. So this is 1.4 times our dead loads. And we've got two dead loads. We've got dead from the roof and dead from level 4, or 36.96 plus 79.8. Ultimate dead, live, and snow, we've got 1.25 times 36.96 plus 79.8 plus 1.5 times our live load reduction factor times our live load of 67.2 plus our snow load times 1. I'll have to write that. I'll give room for that right here. And then ultimate dead snow live. I wonder if I have a better black pen here. My black pen is dying. We have our 1.25 times our 36.96 plus 79.8 plus 1.5. Now our snow is the principal load, so our 31.36 plus our 1.0 times our live load reduction factor times our live load. Okay, now we can plug these into our calculator. You can see it starts to get kind of complicated, and this is why using an Excel sheet can be very handy. So 1.4 times 36.96 plus 79.8. We get 163.5. 1.25 times 36.96 plus 79.8 plus 1.5 times our live load reduction factor times our live load plus our snow factor times our snow load gives us 267.2 kilonewtons. And then our snow and live is 1.25 times 36.96 plus 79.8 plus our principal load factor for snow times our snow load plus our companion load factor times our live load reduction factor times our live load equals 252.9 kilonewtons. So up here, we found that CF here was 93.24. And for this section of the column, CF is 267.2. All right, so we found two sections of our column. We still have two more sections to figure out. We've got loads of time, so I think this is fine. All right, now we want to do the column from level 2 to level 3. So from level 2 to level 3, it is not supporting level 2. It is this portion of the column, and it is picking up level 3, level 4, and the roof. So supports roof, level 4, and level 3. We know that the dead load of the roof is 1.32 kPa, and the tributary area is 28 meters squared, and that PD roof is 36.96 kilonewtons. We've already calculated that. We know the snow load roof is 1.12 kPa, and the tributary area is 28 meters squared, and the P snow roof is 31.36 kilonewtons. We know the dead load from level 4 is 2.85 kPa, and the tributary area is 28 meters squared. So P dead level 4 we already calculated as 79.8 kilonewtons. The live load from level 4 was 2.40 kPa. Our tributary area is 28 meters squared. And our P live from level 4, 67.8 kilonewtons. Now we're adding in level 3. Our dead load from level 3, we calculated last week that all the floors had a dead load of 2.85 kPa. We saw this week that our tributary area is the same on all the floors for this example, but it doesn't have to be. We could have examples where they have different tributary areas. Is 28 meters for this one. So P dead from level 3, well, it's the same 2.85 times 28 meters, so it's also going to be 79.8 kilonewtons. Our live load for level 3 is 2.4 kPa, our tributary area is 28 meters squared. So P live level 3, it's the same 2.4 kPa times 28 meters, so it's 67.8 kilonewtons. So we've increased the amount, we've increased the amount of dead load and we've doubled the amount of live load. But we've also doubled the tributary area of live load. So we're going to have a different live load reduction factor. Live load reduction factor is 0.3 plus the square root of 9.8 divided by the tributary area of the live load. So we've got this live load of 28 meters squared and this live load of 28 meters squared. So we've got 28 plus 28. So we can calculate this live load reduction factor. I apologize if any of you can hear my tummy growling. 9.8 divided by 28 plus 28. And we get a live load reduction factor of 0.718. The reason I'm keeping a lot of significant figures here, I wouldn't normally do that if I was doing just hand calculations, but because there's an Excel file that I want it to match perfectly for you, I find that if I round in this and do perfect calculations in the Excel file, and we end up with 0.1 or 0.2 or even a kilonewton difference, people get really upset. So I'm going to keep a bit more significant figures here than I normally would, just so that we can get a really close answer to exactly what the Excel file has. In assignments and the final exam, I do both, where I keep an extreme amount of significant figures, and then I do it where I do a lot of rounding, and I make sure that the answer has a buffer built into it in case you do one of those two extremes. All right, so let's figure out, this might be easier. Let's figure out what our total dead load is from level 2 to level 3, because we have 36.96 plus 79.8 plus 79.8. This might just make our load combination calculation a little less messy. So we have 36.96 plus 79.8 plus 79.8. We get 196.56 kilonewtons of dead load. P snow load from level 2 to level 3 is still just the same load we picked up on the roof. And the live load from level 2 to level 3 is our live load reduction factor times our live load from both floors. So 0.7183 times 67.8 plus 67.8 equals 97.4 kilonewtons. All right, ultimate dead load is 1.4 times 196.56. Ultimate dead live snow is 1.25 times 196.56 plus 1.5 times our live load. I've already put my live load reduction factor into that, plus 1.0 times my snow load. And then ultimate snow live. What do you think? My snow hasn't gone up and my live did, and in the last one, live is the principal load and snow is the companion governed. I know, just from looking at this, there's no way this one's going to govern. I'm going to do it this time because I want to show you the process. But when we do the next floor, I'm not even going to bother to calculate this one. All right, 1.25 times 1.96, 196.56 plus 1.5 times my snow load plus my companion load of live with the live load reduction factor already built in. Okay, dead, factored dead. 1.4 times 196.56 equals 275.2 kilonewtons. 1.25 times 196.56 plus 1.5 times 97.4 plus 1.0 times 31.36. 423.2 kilonewtons. 1.25 times times 196.56 plus 1.5 times 31.36 plus 97.4 is 390.1 kilonewtons. So I'm just going to double check that this matches what I have. What did I do different here? 7.5. I have that different in my Excel sheet. Why? 67.2. Just I want to make sure I match exactly what you guys have in the so 90. This is slightly different, and that is live load reduction. Oh, did I? 28 times 2.4. What a pain in the butt. Okay, don't curse me too much. All of those 8s for live should have been 2. You guys probably noticed it right away, and if we were live in person, you would have yelled at me while I was up on the stage, and I wouldn't have made such a ridiculous mistake. The process is sound. Don't worry about it too much. This should have been 67.2, and this should have been 67.2. That 0.6 means that this value here is out by about 1.3 kilonewtons from the actual answer. This is why double checking things is so important, and I was double checking it. I knew right away that something seemed weird here. So I have an Excel file. I've also done some stuff by hand. This is why for this assignment, I want you guys to talk to each other, compare answers. Don't say just give me your answer, because what if they did it wrong? You want to check it yourself. Okay, so I was pretty darn close to this. I made an oopsie. So this should have been 421.9 kilonewtons because of this and this. Okay? So from level 2 to level 3, CF equals 421.9 kilonewtons. All right, we have a final one to check. What is CF from ground to level 2? We want to figure out what that is. So column ground to level 2. So this supports roof, level 4, level 3, and level 2. So we've got all of those going on here. All right, well, you know what? I've already figured out all of these. I'm just gonna add, I'm gonna put, well, let's go through it. Dead load roof, it's 1.32 kPa. The tributary area equals 28 meters squared. and P dead roof equals 36.96 kilonewtons. Snow load roof equals 1.12 kPa. Tributary area equals 28 meters squared. P snow roof equals 31.36 kilonewtons. Dead load level 4 equals 2.85 kPa. Tributary area equals 28 meters squared. And P dead level 4 is 79.8 kilonewtons. Live load level 4 is 2.4 kPa. Tributary area is 28 meters squared. And P live level 4 is 67.2 kilonewtons, not 67.8 like I screwed up in the last portion of it. All right. Dead load level 3, live load level 3, dead load level 2, and live load level 2. 2.85, 2.4, 2.85, 2.4. Tributary areas, all 28 meters squared. P dead level 3, P live level 3, P dead level 2, P live level 2. 79.8, 67.2, 79.8, 67.2, all in kilonewtons. Whew, shake my hand out. Okay. Let's add up all our deads and all of our lives. But before we do that, let's take a look at our live load reduction factor now. We've added another 28 meters squared of live load. So live load reduction factor equals 0.3 plus the square root of 9.8 divided by 28 plus 28 plus 28. Because we've got our level 4 live load, our level 3 live load, and our level 2 live load. Remember, the tributary area doesn't need to be the same on all the floors or for all the loads. In the example you're going to do on the assignment, you're given different tributary areas, I believe. Okay, let's calculate this tributary area. We've got 0.3 plus the square root of 9.8 divided by 3 times 28. And we get 0.6416. Okay. P dead from ground to level 2 is our 36.96 plus 79.8 times 3 times. We had it 79.8, 79.8, and 79.8. Our P snow from ground to level 2 is just that same snow load that we had from the roof. And our live from ground to level 2 is our live load reduction factor times 67.2 times 3 times, because we had 67.2 all 3 times. So our total dead load is 36.96 plus 79.8 times 3, or 276.36 kilonewtons. And our live load is 0.6416 ARC1046 times 67.2 times 3, or 129.35 kilonewtons. Let's look at our load combinations. Dead by itself is 1.4 times 276.36. Have you guys noticed that we haven't had the dead govern on its own yet? Well, dead, that one often governs for construction situations, or if we have a concrete roof with nominal snow loads on it. So if you were designing a concrete building in Florida, this load combination would probably be what governs. It just tends to not be what governs here. Ultimate dead live snow. I'm not even going to do the snow live because we saw that it hasn't really governed, and we haven't added more snow, but we have added more live. Plus my live load, so 1.5 times 129.35 plus 1 times 31.36. Okay, the dead. 1.4 times 276.36 is 386.9. And our factored load with dead, live, and snow, 1.25 times 276.36 plus 1.5 times 129.35 plus 31.36 equals 570.8 kilonewtons. Okay, so we now know that up here we have 570.8 kilonewtons from ground to level 2. So we now have a pretty good idea of what our factored load is on this column. So that means for this column here, we need a column with a reduced capacity greater than 93.24 kilonewtons. Down here, we need a column with a reduced capacity greater than 570.8. This is why columns will often get smaller as they go up the building, because you can save a little bit of money that way. So I've just gone through one column here step by step. It took about 2 pages to do the calculations. I have worked out for you completely another problem. So that was column C1. I have it worked out again with column C3, and I've also provided you the Excel sheet. Feel free to go through and do everything I just did by hand if you are the sort that feels like you need a little bit of extra practice. If you feel like you've got a good handle on it, you don't have to do that. But this is to give you the opportunity to go a little bit further. What I've been trying to do is add more examples for worked out examples for people. We don't always have time to go through them all in person, but I want to give you the opportunity to have a lot of resources. So this picks a different column with a different tributary area that you can go through. Get the system down and then try the one on the assignment. But again, remember, talk to your colleagues, talk to your peers during that assignment. I have no problem with you guys communicating with each other. In fact, I encourage it. Try not to just copy each other's answers. Do the work, because the only person that's gonna suffer is you. I don't mind giving you the marks. But in the exam, when you don't have time to communicate and you're given different versions of problems, you won't know how to do it. So this is really just about you. You guys are big, you know how to look after yourself. I'm not gonna make sure you don't cheat for something like this. But try to make sure you do the work, because that's gonna be what helps you retain it. Now, I'm going to tell you that you're not going to have ones this complicated. Even your project one isn't going to be quite this complicated. You will have to do this in your project for your column, though. And we're going to do a little bit more with it. We're actually going to learn over the next couple weeks how to draw a pretty picture that tells us what's happening in this column. Because this chart while helpful, it might be nice to see a visual graphic of what's going on in this column. Hopefully, where you guys are in an architecture program, you will really appreciate the visual side of it. And so that's going to come in a little bit. Okay. What are the takeaway tips? This lecture's on the shorter side, closer to the 2-hour mark, because I know last week's was a really long lecture. And I want to give you a little bit of a breather. I like them to be around 2.5 hours. And so over the 2 weeks, it kind of balances it out. It's hard that there's not a good place to stop. You have to kind of get through a set of information. So, forever, you should remember that there are more than the standard loads. You can have pre-stress, you can have temperature loads. It might not be what impacts you all the time, but it might be something that you need to talk about with your engineer. We factor the loads and reduce the capacity of the material. We combine all the factored loads to find the worst case factored load. We also combine unfactored loads for serviceability. Different elements could have different worst case combinations. So we saw that our column from level 4 to the roof was governed by the dead and snow combination, where the other floors were governed by dead and live as the companion with snow or live as the principal and snow as the companion. Okay. For studying, you should know how to do soil pressure on a foundation wall. I give you one of those in the exam. I promise you there's going to be one of those. But I give you all the information. So just follow that formula and you'll be fine. You should understand that factor of safety exists, but we don't use it now. There are times and certain codes that do use it, and that's why I like to mention it. I just did something yesterday where I had to look at the factor of safety on something. You should understand what ultimate limit state design is. You should know that serviceability limit states exist within that for different types of load combinations. And you should know how to calculate the worst ultimate limit states load case, because we're going to need that when we talk about CF and TF and VF and MF in the coming weeks. Okay. Next week, we're gonna start doing really cool shit. I've talked a lot about how everything you need to know about structures, you already know. Next week, we're gonna start to really explore that and then see how we can mathematically represent what we already know. Some of you are gonna get intimidated by the math, but if you just stop and think about what the complicated symbols are I'm drawing, that it's really just shorthand for something we already know in our head, okay? So sometimes they're gonna look complicated, but they're not. It's really simple stuff, and we're gonna stop and talk about it and think about it. And I've tried to break it down in kind of a process that gets us to where we need to be. So next week, we start talking about statics, which is really fun. Okay, see you next week.